здесь альфа длиннее, чем бета.
Вот так
я их
представил.
Да,
просто...
Я вот как бы воспользовался этой симметрией, чтобы нарисовать BC на самом деле.
Ну да.
У них что, полная классификация есть у этих систем корней?
Да, мы сюда их, собственно, и ведем.
Эти буквы
А, Б, С, Д,
Да.
эти ешки, и вот это же туи.
Алфавита хватит.
Ну вот,
Всего их нет.
Тут уже вон две буквы используют.
Сейчас.
Так точно.
Нет,
но Ж это последний.
Да. Ну там 4 основных линии, по-моему, и еще 2 или 3 прерывающиеся, да?
Да, Е, Ф, Ж, это исключительно.
У них такое исключительно.
Ну потому что они не для каждого.
Не тут все, Ашек их бесконечно много, там 1, 2, так далее.
А, Б, С, Д их много, да.
И что, все некоторые алгебры Ли соответствуют?
Да.
Ну,
ДН это СО2Н.
Ну, это как бы это прям классификацию берет. Не то, чтобы это каждая нектор соответствует, но любая полупростая алгебра Ли соответствует некоторой диаграмме D.
Я тебе говорю, там теория представления очень хорошо изучена.
Да.
Не, вот это, конечно, удивительно для меня было, что я вот узнал, что, оказывается, все эти представления, они могут быть не очень полиномиальными.
Не будем останавливать трансляцию.
Ощущение, что мы в прошлый раз что-то не доказали, и сегодня мы этим прям жестко пользовались, да?
Мы теорему сформулировали. Не, мы чем пользовались? Мы пользовались тем,
во-первых,
только вот тем, что неприводимая система получилась. И то. Ладно,
вот как минимум вот этим мы пользовались, да, очень жестко.
Ну все, больше ничем.
Еще чем-то сейчас. Тем, что еще сейчас мы доказали, разве что же альфа равномерно.
Да, доказали. Через представление следа.
Да. Я не помню, по-моему, как это мы...
Нормально мы это показали. Я, правда, не помню, что показали.
Нет, я помню, что была вот эта вот какая-то там пляска с этими представлениями, с регионами.
Что ты говоришь, что теория представления, если она простая?
Ну как, проще, чем...
Я вот сегодня смотрел, там же теория представления Слена то же самое, что исчисление Шуберта, по сути, да? Ну, если мы тензорное произведение хотим раскладывать.
Стандартная таблица.
Ну да.
Я не знаю, что такое исчисление Шуберта, мне это многие говорят, но я вот не понимаю.
Пересечение космоня.
Ну это я вот не знаю.
Это то же самое, что вот эти коэффициенты Литтл-Вудер-Черцов.
Что? Что это такое?
То есть мы два неприводимых представления. Да. СЛ. Или же L. Да. В лямбда, в мю. Возьми их тензорное произведение.
Да.
И разложи его на... Оно раскладывается на сумму неприводимых. Вот пятикратности вхождений неприводимых в это тензорное произведение, это как раз и коэффициенты есть.
Значит, стандартная.
Я просто сегодня смотрел, сегодня и вчера, там какой-то алгоритм приводится для, вычислять не совсем эти коэффициенты, а пересечением нагросменяния. Но оно выражается через эти коэффициенты. Там, короче, нагросменяние 5-10, то есть в пятимерных пространствах, в десятимерном, пересекаются какие-то циклы. И вот эту хрень забили на компьютер, и там считалось, по-моему, 216 часов. На достаточно маленьком расменянии. Что вообще может там 216 часов считаться? А ты говоришь, что все просто.
Ну, с точки зрения именно такой.
Все просто, если это, ничего не считать.
Так а зачем что-то?
Как обычно, если все теоретически рассматривать, то все просто. А как нужно что-то посчитать, то вообще непонятно, как делать. берете, отписываете.
А что, так бывает?
Вот даже список людей, у которых такая проблема.
Нет, 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 нет.
У тебя тут нет. 257.
Вот сейчас сколько?
247.
А, это плохо?
Должно быть 250. 240, 245.
Сейчас, сколько там у народа? Я видел что-то 255 у кого-то.
Да.
257, это чего что такое? Точно, рейтинг формят люди, я понял.
Что, это рейтинг может как-то?
Да, это поднимает рейтинг, конечно.
Я вот не знаю.
Ну, типа, если ты на куче курсов получаешь, ну, слушай, непонятно, что рейтинг как считается.
У тебя же
Это
диплом, у тебя в диплом рейтинг не пойдет.
Да, но, короче, у тебя сумма кредитов плюс умножить на вес курса, это вот твой рейтинг.
А оценка влияет?
Ну да, я тебе говорю, оценка за курс умножить на количество кредитов. Ну, всякое, если у тебя как бы на один курс больше, ты получаешь плюс школьный, понимаешь, рейтинг.
Мощно.
Там не усредняется, вот, понимаешь?
Ну, короче, отписался от хардклассов, но ходить буду. Потому что, ну, контрольные ты заранее.
Мы больше иногда учим контрольные.
Okay, so let's start. Again, I need to maybe to remind, so definitions. So I have root system. So what is a root system? It's a finite subset of Euclidean space. Right, so reminder. I don't know. We just talked about this on the seminar, so just to reference to something. Let me put it on board again. And the defining properties are first R span E, spans E, then if I have alpha and beta right in R, then S alpha of beta is also in R. This is a reflection with respect to root alpha. And the third one is that, maybe this is the third one, and okay, this number is integer, and if additionally I have that for any, if alpha and beta are roots, right, such that alpha is C beta, then C is plus minus 1, then R is called reduce. And we had this proposition. I don't know if I want. Okay, let me try to use this board. So proposition is the following. First, we need to organize an Euclidean space, right? This Euclidean space, potential Euclidean space, will be IHR star, right? What it is? It's real span of roots. Right, should I write like this? So this is bold R, this is usual R. So proposition goes like this. So first, denote HR star to be the linear span of roots. And also I would like to have a form, right, on H star, right? It's a form on H star given by the Killing form. Then restriction of so this restricted to H star R is positive definite. And by the way, it's non-degenerate, right? So this makes H as R star Euclidean space with this inner product, which we'll denote by the same parentheses. And second is that R is an abstract root system in H R star. Yes. So sometimes if I have root system in E, people say such a word as rank of R. This is just dimension of E. Okay. All right. So let's prove this. First, I would like to prove that n alpha beta is integer. Proof. Okay. So we will use this. Actually, it should be is real, right, and positive definite. So integers are real, so that I would like to use this. But I would like to prove first that n alpha beta is integer. Right. So recall this, first of all, SO2 triple. Right, so this is span over C of E, F, and H alpha, where E is in G alpha, F is in G minus alpha. And for them to be standard generators of SL2, I also would like to say something about the killing form of INDEF, but I can stop like that. Maybe they have some different commutation relations. Anyways, so why this thing is integer? Because it is a weight of this SL2 in some irreducible representation, finite dimensional. So that's the idea. So which representation? So let's recall that we had this V alpha beta, right? And this is direct sum of G alpha. So here this is triple corresponding to alpha. So I think should take like this. And K is in Z. So recall that this is an irreducible representation of SL2 alpha. All right. So I would like to say that so n alpha beta is so I would like to notice that V that n alpha beta is weight in this weight subspace. All right. For that, I will need to choose K somehow. Right. So let me see what I was writing this. So which particular weight? Right. Yeah, so both alpha and beta are yeah, so I claim that so if this is mu, so let me call this mu. I claim that V alpha beta mu is exactly G beta. I think we computed yes, I think we computed it last time, but still. So let's see. Yes, this weight subspace of this weight. And by the way, I'm not even care if this is zero-dimensional, one-dimensional, right? I just need this to be in Z, right? So let's see. So what does it mean? It means that so if I take G beta, right, and take H alpha and commutator with some elements in G beta, right? Was that? Yeah, it can be. Yeah, then it's not weight though. Sorry. I really need this to be weight in here, right? So I would like it to prove that it's not zero-dimensional. But first, let me see. It's not zero dimensional, right? You're right. So because beta is root by our assumption, yes. Right. So now we just need to see that if I commute with some element, right? Then right. So if I have some element x from g beta, right? Then I would like it to be well, mu, right, x. So let's check it. So this will give me beta of h alpha, right? And we are done by definition of h alpha because it's 2 beta alpha over alpha alpha. Yeah, so I proved for this one, right? So this one is n beta alpha. Right, so again, beta is a root. Therefore, g beta is not 0. So therefore, mu is weight in v alpha beta. Therefore, mu is integer. Agree? Okay. Now let me use this. Okay. So I will need a bunch of observations. So let me take gamma and alpha two roots. Then gamma of h alpha, right, is exactly n gamma alpha. And this is, as we proved, is integer. In particular, it's real. Right? So gamma of h alpha is real. Let's remember this. So first. Second is the following. So now let me take gamma again from R, but alpha is from just h star R. Then again, just it's just immediate from the first observation that again gamma of h alpha is in here. So no, I would like it to be real. I'm a little bit confused because small h alpha is it's only for we did
We define it only for roots.
for roots.
And it
Right.
would be
So maybe I would like to do it the other way around.
also could not
Yes, yes. So that's my confusion. Let me maybe try to. Yes, yes. That's what we would like to do. Right. So I can do like this, right?
Yeah,
This makes sense.
but that's kind of
What is H gamma?
H gamma is, so with gamma is root. The,
I don't understand what's the problem with it being real, because we actually checked on the basis already.
no problems. No problems now.
H alpha.
Yeah. So when I change it like this, no problems. It kind of messes up what I did when preparing for lecture. So let's see if actually I was stuck or not. So let's see. Then I have this. All right. Maybe I don't even need capital H alpha. Do I? Right. So I would like to do the following. 1 second. Let me see what do I need. No, I really need H small, because if I change it to H capital here, I cannot say that it's in R anyways, because I didn't prove that alpha alpha is in R. Let me see if I can show then one second. Well, of course, if I have two roots, right? So let me try it this way. So maybe let's try to forget this. Let's see if I can proceed without losing too much time. If not, then we'll skip and return to this. So so let me take alpha beta from the root system, right? Then let me try to compute the killing form of H alpha, H beta. It's by definition trace of A at H alpha at H beta, right? But this is sum. So H alpha and H beta, I can simultaneously diagonalize them, right? So I claim that this is sum over gamma from R. And then I should say gamma of H alpha, gamma of H beta.
Why over R? Because R can be like dependent, linearly, right?
No, yes, yes. I just go over diagonal, right? Over eigenvalues. Yes. Very well. So no questions here, right?
Yeah, why?
Why? Because this is diagonal matrix with eigenvalues gamma 1 of H alpha, gamma 2 of H alpha, and so on, where gamma i's are roots. What is a root decomposition? It's decomposition in eigenspaces of H i's. And for this is the same.
Just some zeros, yeah?
Some zeros, but we don't care because it's trace, right? So it doesn't count as zeros. Right, so this is then in Z. This is then in Z. Right? And therefore, this is in Z. So therefore, Killing form, right, restricted to H. So for any two elements, say H1 and H2, if H1 is in so H1 and H2, they're any elements of H star R. Sorry. Yeah, so again, so any element from the cartan is diagonalized in some basis, right? And we
Use that H alpha only in H.
yeah, I didn't. Right. Well, I use it that it is H alpha to see that it's in Z. Right. So it means that right. So now I would so my goal is to see that yes, without star. Yes, it's positive definite. Does it give us? So maybe I don't want to erase this. So maybe. So we all remember what is root system. I can erase this. Okay, right. So we said that killing form. So if I introduced HR to be the real span of H alphas, right? Right, as alpha is in R. Then the killing form, right, restricted to HR is real. And actually, it's real and positive definite, moreover, right? Because just using the same computation, now I have two alphas, right? Suppose that I have. Then I'll just have square of gamma of H alpha here, right? Just using this. Right, right. So I should compute K, H alpha, H alpha. Right, so that's true. So if I take some linear combination, let me see. So if I take just any, so let's check. I don't know. Somehow everything. So if I have KHH, right? Right. So it is sum over K H alpha H beta with some coefficients, right? C alpha C beta, right? And alpha and beta is from R, right? But this doesn't give us too much because we don't know, right? If we have cross terms or not. Okay, so let's not, I don't know, I have to think about this. I don't know. Don't want to spend too much time on this. So something doesn't work.
So we proved that it is real, right?
Yeah, we proved that it is real on HR, but we would like to prove that it's real on HR star. Still some argument.
So we have to prove that K of H alpha but is positive, but for big H, right?
Yes, for weak H.
Why?
Well, because alpha, so you have alpha beta is by definition K of H alpha H beta. Right, and so this is what I would like to prove that this is real. Yes. So if I take okay, so again, let us this will be my work for next time. So okay, this happens. So let us then prove. So we don't know if so we know that it is positive definite. We didn't prove it, but it's true. So let us discuss it next time. But what do we need to prove that it's root system? This we proved, right? R spans E. It's just by definition, and so we need to prove second and fourth. So let's do this.
Why is it square? Isn't there should be
Okay, so you proved it. I don't know. I'm kind of stuck here. So again, what is your argument? Right, right. So this is like this. Right. So gamma is from R, and alpha beta is also from alpha and beta and gamma from R. So here it's beta, right? So it is sum C gamma of C alpha H alpha, right? Gamma C beta H beta. So here it's alpha beta gamma from R. Right, this is yes. write this, and right. Right. But this one is real. We actually, yeah, because C alphas are real, gamma of H alpha is actually integer, right? So therefore, K restricted to the Cartan subalgebra, to HR, right, is real and positive definite. But we need. So I think saying that this can be 0, right? No, the killing form restrict. So yes, it's non-degenerate doesn't mean that this cannot be 0. Yes. Okay, again, so let me think. Right, so now let us try to prove that if I have alpha and beta from R, right, then I have, so S alpha of beta in R is in R. Right, so again, we use presentation theory of SL2 for that. Right. So we have beta, so G beta is not 0, right? Again, the same argument as before. So mu, right, which is 2 alpha beta over beta beta is a weight in V alpha beta. Yeah, G beta is not 0, because it's a root. Right.
The part that we want to prove that this is not equal to 0.
Yeah.
So we know that gamma of H for any gamma from H star is real, yeah?
For any gamma from R, for any H from H star. For H star R, yeah.
Yeah, it's real.
From HR, yes, it's real, yes.
Okay, so killing form is for H. H still lies in Cartan subalgebra, so it's still semi-simple. It's still diagonal.
Yes.
So there will be still something like trace of at H multiplied by at H, so it still will be some gamma of H.
Yes. So that's what we. You're saying directly from here.
I think that gamma of H should be positive.
No, actually, yeah, it's obvious because gamma is not 0 functional. It's not 0 functional, then there should exist some alpha.
You're saying that let us write this as follows. Gamma of H, gamma of H.
Yeah, and gamma of H is some real number. So
yes.
if there exists some gamma that's not 0 on H, this should be positive.
Yes.
So, and there's exists since H is not 0.
H is not 0.
Then there from root.
Yeah. So this is over all gamma in R, right? So we should find. So if H is not 0, this is something that we solved in the seminar, right?
Spans H, spans over algebra.
Yes.
R. Then there exists some of gamma.
So if this gamma does not exist, right? Then add h is 0, and h is in the center, and the same argument is from the seminar. Yeah, it works. Yes, so we're not using this. Just because h is in HR, right? It's like this, which is inside H as well. So this is again gamma 1 of H, gamma 2 of H, and so on. It's a diagonal matrix like this. What?
That's at H.
Yes, yes. It's kind of by, it's image by under adjoint representation, right? So the same argument is there. Then we have this, right? Just by definition of the, sorry. so this is trace of add H, right? This is exactly what I wrote. So add H, so the diagonal element of add H times add H is gamma of H times gamma of H for some root gamma. And then I sum over all roots. It's the same exact computation that is for this one. We never use that at this H alpha or H beta. That's the point. Right.
Yeah, but actually we only use it to prove that it's the form is weak. Once we know that the form is weak,
Yes, yes.
Well, we use for saying that gamma H is real.
So okay, are you satisfied, right? So we have this. So therefore, it's sum of squares, and of course, in one of these terms, at least in one of these terms, is not 0. Okay. Otherwise, H is in the center, and it is 0 then. So the Killing form is on H R is positive definite. But why it's the corresponding form on H star R is positive definite? It's another. So we have to deduce something. Yeah, so you take isomorphism, but you should be careful. So this is isomorphism of H and H star, right? Yes. So you take you're saying KH alpha with H beta is the same as beta of H alpha.
Yes, yes. Then we can.
And this is integer.
Yeah. Then you can try to rewrite H small alpha on the left as through H beta.
Okay, so this will be H alpha.
K of H alpha divided by 2 multiplied by.
Yes, this is this, right? So it will be 2.
No, I mean H big.
H big.
H big. I'm very sorry. H.
Yes, so this one is H beta times beta beta over 2, right?
Yes, and then we have beta beta equal to ratio of beta of H alpha, which is integer, to K of H alpha H beta. So multiplied by 2.
Whatever. So this becomes a seminar. So, anyways, I'm okay. I'm okay with that, because I mean, what's the point in me just saying everything perfectly when you can work this out? Say it again. Да, да.
Изоморфизм, он в больших H работает. У нас перенаписался на маленьких пространствах. Отличается перескалированием на модуль H. Модуль H вообще непонятно какой. Модуль H квадрат.
Ну да.
В этом проблема.
Okay, so what's going on? So we have so this is the same as this one, right?
And then take beta equal to alpha.
Right, but take beta equal to alpha. Then what's going on? You have k of h alpha.
Yes, which is positive.
Which is positive. Right. Times alpha.
Yes, and
So therefore alpha is positive.
but we should note that it's not just integer, it's just because alpha of h alpha is.
Yes.
So we take beta equal to alpha, yeah?
Yeah.
Yeah, that's what's written
I just
here.
took beta because I started from kind of definition of h big beta.
Right. So we proved first of all that alpha with alpha is positive. Right, but we also need that alpha and beta is real. Yeah, we'd like to prove that alpha with so this is an important step.
Weights are integer.
Yes.
We multiply them by positive numbers.
So these are kh alpha h beta, right? And then this is k of h alpha h beta. Maybe you wrote it somewhere, I don't know. Times 4, right? Alpha, beta. So this is positive. Anyways, it's real. This one is real. This one is real. Therefore, this one is real. Maybe you're right. Anyways, doesn't really matter. It's real. Two is real. Thank God. 4, yes, sorry. Anyways. All right. So we proved the first part with the help of everybody. Should we organize it somehow, or just let's just have it like this, right? But again, the crucial part is to write killing form like this, right? And then just some algebraic stuff. All right. So now let us see this. Okay, this we erase.
But mu is, I guess, in this notation is weight of the beta alpha. We should.
Right. Maybe what was it like this, right?
I guess yes.
Is it still here? No. Right. So let me consider V alpha beta of this weight mu right? So I would like to see that this is a root, right? So I would like, so I claim that G S alpha beta is this. So since this weight subspace is not zero, so this is V alpha beta of mu, right? This is non-zero, right? We know from representation theory of SL2, if I have some subspace of weight mu non-zero, then we have symmetric weight for sure, right? So therefore, this one is also non-zero. So we would like to see if this equals to this. So we just need to check, right? We take H alpha, right, and commute with something from here, right? So this lives in GS alpha beta. This gives me what? S alpha. Yes. So let's recall what is S alpha. S alpha applied to beta, right? It is beta minus 2 alpha beta over alpha alpha alpha, right? So I have S alpha beta, right, applied to H alpha, right, to X. Right, so I would like to compute what is this thing. Right. So we actually, yes, so let's compute. Then we have this. So I have beta of H alpha minus 2 alpha beta divided by alpha alpha, and then alpha of H alpha. So this thing is 2, right? So what I'm writing is actually this. This equals to this. So this is 2. Alpha of H alpha, right? So this guy is exactly what's written here, right? So it's 2 alpha beta over alpha alpha minus 4 of this. So it's negative 2 alpha beta divided by alpha alpha. So it's negative mu. So we proved this. And therefore, we proved that also S alpha of beta is also root. That's the point. I would like to prove. So first of all, I would like to prove that this space, whatever 0 it is or not 0, it coincides with this one. So suppose I take a vector from it. Yes. Maybe it is 0, but still everything is.
It's not really good to talk about weight subspaces and zeros, because zero is
Yes.
The representation theory of how did you take x from v alpha beta? Oh no, sorry, not v alpha beta, but v alpha beta minus mu. This is not zero.
Right. Yes, yes. Yes, you're right. Actually, we should do the following. We should take this one, right? We should take v, which is not 0, from this one. This is not 0, right? Sorry. Then let me apply, no, like this. So this I can, there is some v such that it is not 0, right? This computation we still need. Then let me apply f, which is the f from SL2 triple, 2 mu times to it. No, so then this to v. So this will belong to v alpha beta negative mu. Sorry, even mu times, right?
Yeah,
It shifts the weight by 2.
Yeah, actually, if mu is negative, you should apply b times.
If mu is negative, yes, that is true. So we can assume without loss of generality that it's positive. Okay, if negative, then we apply. Then by representation theory of SL2, this is also not 0.
Yeah, but I think we just proved that v alpha beta minus mu is not equal to 0. We just
Yeah, I think there is some problem with the proof because we take x from GIS alpha beta, and what we won't take, I think we won't take x from the alpha beta minus mu.
No, what Nikolai suggests is take. So okay, we have v alpha beta mu. We know that this is also not 0. So take a vector from here, and then this will be from a vector from here.
Apply arbitrary h from
Yes.
get the same
Right, and this gives us that yes.
lies inside.
all our computations should be like vectors.
Yes, I agree. So again, so let me clean this up. Yeah, sorry. Today's lecture is hectic, but I don't know. This happens sometimes. It's pity that I wanted to do more. Right. So what do we have? So we know that v alpha beta of negative mu is not 0, right? So let me take x from here, right? Since x is from here, it means that h applied to x, right, is negative mu x, right, just by definition. But h applied to x is just, it's a joint action. Right, so we have at h, so h with x is this, h with x, yes. But then we know that negative mu, right, going backwards, right, negative mu is exactly this, right? So this is the same as S alpha of beta of hx. So therefore x.
I think you need to apply mu to something. I really don't understand how it.
What do you mean apply mu? Mu is a number.
Mu is to
It's a weight of SL2 of a representation of SL2.
well, it is equal by
No, so this is also a number. So this I apply to h, and this gives me a number.
suppose we wanted to apply it to h alpha.
Yeah, the problem. How do we apply it to arbitrary?
No, to arbitrary h.
I think we wanted always wanted to say that
Ah.
it's h alpha.
Yes, you're right. Yes. So let's see. Well, let's see what happens here.
Spans whole.
Yes, that's exactly what's written here. So
Yeah, but
yeah.
since h alpha spans whole Cartesian algebra, it works for every. So I suppose from this we can denotate that g s alpha beta is equal to e alpha. Well,
Yes, yes.
denotate, but I say that from this we can denotate that s alpha beta is lies in root. It is
Right. So here alpha is some is one, but we can do it with every root, right? Since h alpha span h, right? This means that indeed. So this is for every alpha in R. So x belongs to G S alpha of beta. So x we chose to be non-zero, so therefore we're done. Okay. Whew. So now let us prove that it is reduced. Mm-hmm. Sure. Yes. So we cannot. No, but still, like, why? So if I take some other. Okay, let's try to fix this. So if I take, so I would like this to be for this line, right? To be for every h alpha. Right. So I would like this, but still, why? So if I take different root. Why cannot first I fix root, right? And then I take v alpha beta. So when I take another root,
yeah, but
I take another v alpha beta.
I want to prove that g s alpha beta, just that s alpha beta is lies in root.
Ah, yes, yes.
And what we want to say that h with x, with any x from this, any h with any x from this, acts like s alpha beta h.
The proof was that g beta plus k alpha is the same that v alpha beta from mu plus 2k.
Mm-hmm.
So which is nothing.
Yes, yes. That's what we. So beta plus k alpha. Sorry. G beta of plus k alpha. V alpha beta, and then what? Mu plus 2k. Yes.
So
S-
s alpha beta.
So we should take k equal to minus mu, right?
Yeah, but
So let me take x from here. Yes, yes. So this one is not 0, right? So this is g beta minus mu alpha. But I claim that beta minus mu alpha is actually S alpha beta. Yeah, then we are done. Right. Maybe we are done. I'm not sure even anymore. So okay, we tried to fix it. So this is proved for every k.
Yes. So what we proved? We proved that g s alpha beta not equal to 0. That's fine. Why is it root?
Because that's by definition what is root. If g alpha is not 0,
That's just alpha.
then alpha is root.
That's by definition g of alpha. Yeah.
Okay. So sorry. Again, once again. So we have this. So the statement is that we had this last time, but we can check if you wish. Okay. So now v alpha beta mu is not 0 because it's the same as it's g beta, and g beta is root. So therefore v alpha beta negative mu is also non-zero. But g alpha beta negative mu is this, according to this line. Then beta minus mu alpha is exactly the reflection of beta with respect to alpha. I don't know how cool is that, but I guess I should have my. So I prepared this notes like a long time, like maybe a week ago. So I forgot. So maybe I should do it clearer than today. So anyways, so until Nikolai didn't notice any other hole in our proof, we are done. Okay, very nice. So let's. We still didn't prove that it's reduced, though. So let's try to do this. All right. I need now. So what do I want to prove is that. So first of all, if I have alpha and beta are roots, and suppose that alpha is c beta, right? Then according to what we saw today, for example, in the seminar, then C is from this set. Right? Just because both n alpha beta and beta alpha, they are both integers. Right? First part of your problem, yes. Very good. So now let us use that, and actually it's enough to prove that C cannot be 2, right? Because so suppose it's negative 2 or plus minus 1/2, then you can just interchange alpha and beta, or take negative alpha and negative beta. Then you're in a situation when C is 2, right? So enough to prove that C is not 2. Very well. But this we again do by representation theory of SL2. So we would like to see that if alpha is root, then G to alpha is 0. So again, let us consider representation V alpha. It was what? So H, CH alpha plus sum over G K alpha, right? Where K is from non-zero integers. Right. So this is an irreducible representation of SL2 alpha. Moreover, adjoint representation of SL2 alpha is sub-representation here. Because SL2 alpha is CH alpha plus G alpha, right, and plus G minus alpha. It's reducible, and this one is also reducible. So therefore, V alpha is equals SL2 alpha. In particular, G to alpha is 0. Okay, at least this one went smooth. Very well. So yesterday I had kind of something like this when I was going by car to different side of city. Just on every crossroad there was something. Very well. So we proved theorem, did we? Very well. So now let us move, I don't know how much time, so at least let us say something except this theorem, right? So regardless of how much time we have. All right, so today was on the seminar we had a question that how to classify, what does it mean for a root system to be the same, right? Of course, you can, rotate it a little bit, right? So here's the definition of an isomorphism of two root systems. So let R1 and R2 be two root systems in the same Euclidean space. Then define, so phi, some linear map, right, from E to E is called isomorphism of R1 and R2. If we have the following. Well, first of all, of course, phi of R1 is R2. On the other hand, these numbers, right, elements of Cartan matrices, so phi respect these numbers. So n phi of alpha, phi of beta is n alpha beta. I should so this n corresponds to the second root system, this to the first one.
When you say isomorphism of Euclidean space, you mean that it's well, it preserves scalar products, right? Or not?
No, not necessary. So not necessary. I said it's an isomorphism of root systems. So it's a linear map, first of all, right? Satisfying this. In majority of cases, it will preserve, but rescaling, for example, yeah, is okay. Sorry, say it again. Exactly equality. Then they are not isomorphic. Of course, two isomorphic root systems should have the same number of elements. I mean, that's kind of natural, right? I don't know. We might get rid of this and see what can happen, but it's kind of, I don't know what. Usually, if I have a vector space, I usually think about linear transformations. I will have like a simple root system, which is kind of spans R, right? Like spans. So R. I mean, every. So we will need linearity because then we will have simple roots, right? And that's why. Okay. So in particular. Automorphisms of R. These are isomorphisms of R to itself. Now, what we need actually, let's consider some subgroup in here. So definition. Subgroup of automorphisms of R generated by S alphas, where alphas are roots, is called the Weyl group. No. So first of all, these are elements in here. Because of just in the same way as alpha act on E. But we proved that, so it's not even we proved, it's a property of root system.
It's like S alpha beta,
So
goes to S alpha beta, yeah?
Yes, sure. So this is, so these elements in here, so just generate a group. Right. So now let us. So a Weyl group is like that. Let us say something and even try to prove something. Right, so notice, so one obvious thing to notice is that so maybe let's denote it as W, right? That the Weyls group is a finite subgroup of orthogonal group of E, orthogonal with respect to this inner product, right? So these are just reflections. Of course, they don't change angles and lengths. Just because of the morphisms of R is finite. It's a subgroup of this. And R is finite, yes. So next observation is that so let's call it lemma. We will use it in the future for every for all alpha in R. So for every root and every element of Weyl group, we have the following formula S. So if I take S of W alpha is W composed with S alpha and then with W inverse. It's an easy observation, so let's try to check it. Let us introduce notation. So let L alpha be the hyperplane with respect to we reflect when applying S alpha, right? So this is all vectors in E such that alpha with V is 0. Very well. Then let me take L alpha. So we have then, if I apply W to L alpha, is the same. It is another hyperplane corresponding to W of alpha, right? Because reflections, they kind of conserve angles, right, and orthogonality as well. All right. So next observation is that then if I take V, yes. So let's see. If I take so W minus 1 of alpha. So let me see. If I take some alpha and a plane which is orthogonal, right? Right. So it means that I consider all V's such that this is 0. Then if I take W alpha, right, I need to consider WVs, right? So then this is 0. So it seems like it's okay. No, it's fine. So we should check. So seems like okay. Then right. Then let me take V from here. Right. So V is W time W applied to V prime, right? Where V prime lives in L alpha, right? Then I would like to take S alpha, right? Thing that we have here, right? And apply it to V, right? This is the same as S alpha applied to V prime. W S alpha applied to V prime, right? But this is then, so S alpha applied to V prime lives in L alpha. It's V prime again. So W V prime, so this is V. So therefore this element leaves any element of this plane on the same untouched, right? Leaves invariant. Anyway, so this means right, so we have, let me write this down, on LW alpha is ID on LW alpha, right? Right, but we also need to check, so it stays, so this stays the same, right? But also we need to check that where alpha goes. Right.
It's obvious that it is a reflection and this preserves the
Something roughly similar formula.
Where? Which? This formula?
No, a bit higher.
Let me see.
Prime. So WV prime is equal to V.
Ah, that's not prime.
Yeah, that's
That's common.
yeah, that's a comma from up. Everything right.
Right, you have.
Yeah, so this is V. Yes, this is common. Sorry.
Yeah, but
I don't understand why are we not finished.
You have to check on W of alpha.
So it's it is a reflect, right? So it might be.
why is it a reflection?
It might say W of alpha to say.
Yeah, why is it a reflection though?
It's just conjugation of reflection.
Uh, right. So we need to check that it's not identical, though. Right. For that, we need to check how it acts on alpha. It sends alpha to negative alpha.
Да, значит так не может быть. Собственно, от поражения. Да, точно.
Не альфа, а В.
Не, мы хотим сказать то, что S альфа.
Yeah. The W of alpha. It goes to negative W of alpha. Yeah. So again, we check. So it's either identity or a reflection.
How can it be identity if it's conjugation of something?
Yeah, it's conjugation of reflection. So reflection is
Yeah, it's a conjugation of not an identity. Yes, I right. So it's not an identity. Yeah. So yeah, we're done. Yeah, I convinced. Yes. Okay. Very well. So we're done with this. Right. So how much time do we have? No time? Minus many.
Minus 40 minutes.
Okay, so let's stop then. Okay, so hopefully next time will go smoother.